Chapter 14. The modern form of the alchemical quest of the one thing. The study of the properties of the elements shows that these substances fall into groups, the members of each of which are like one another, and form compounds which are similar. The examination of the properties and compositions of compounds has shown that similarity of properties is always accompanied by similarity of composition. Hence, the fact that certain elements are very closely allied in their properties suggests that these elements may also be allied in their composition. Now, to speak of the composition of an element is to think of the element as formed by the union of at least two different substances. It implies the supposition that some elements, at any rate, are really compounds. The fact that there is a very definite connection between the values of the atomic weights and the properties of the elements lends some support to the hypothesis that the substances we call, and are obliged at present to call, elements, may have been formed from one or a few distinct substances by some process of progressive change. If the elements are considered in the order of increasing atomic weights, from hydrogen, whose atomic weight is taken as unity because it is the lightest substance known, to uranium, an atom of which is 240 times heavier than an atom of hydrogen, it is found that the elements fall into periods, and the properties of those in one period vary from element to element in a way which is, broadly and on the whole, like the variation of the properties of those in other periods. This fact suggests the supposition, it might be more accurate to say the speculation, that the elements mark the stable points in a process of change, which has not proceeded continuously from a very simple substance to a very complex one, but has repeated itself, with certain variations, again and again. If such a process has occurred, we might reasonably expect to find substances exhibiting only minute differences in their properties, differences so slight as to make it impossible to assign the substances definitely and certainly either to the class of elements or to that of compounds. We find exactly such substances among what are called the rare earths. There are earth-like substances which exhibit no differences of chemical properties, and yet show minute differences in the characters of the light which they emit when they are raised to a very high temperature. The results of analysis by the spectroscope of the light emitted by certain elements at different temperatures may be reasonably interpreted by supposing that these elements are separated into simpler substances by the action on them of very large quantities of thermal energy. The spectrum of the light emitted by glowing iron, heated by a Bunsen flame, say at 1200 degrees centigrade, which equals about 2200 degrees Fahrenheit, shows a few lines and flutings. When iron is heated in an electric arc, say to 3500 degrees centigrade, about 6300 degrees Fahrenheit, the spectrum shows some 2000 lines. At the higher temperature produced by the electric spark discharge, the spectrum shows only a few lines. As a guide to further investigation, we may provisionally infer from these facts that iron is changed at very high temperatures into substances simpler than itself. Sir Norman Lockyer's study of the spectra of the light from stars has shown that the light from those stars which are presumably the hottest, judging by the general character of their spectra, reveals the presence of a very small number of chemical elements, and that the number of spectral lines, and therefore the number of elements, increases as we pass from the hottest to cooler stars. At each stage of the change from the hottest to cooler stars, certain substances disappear, and certain other substances take their places. It may be supposed, as a suggestive hypothesis, that the lowering of stellar temperature is accompanied by the formation, from simpler forms of matter, of such elements as iron, calcium, manganese, and other metals. In the year 1896, the French chemist Becquerel discovered the fact that salts of the metal uranium, the atomic weight of which is 240, and is greater than that of any other element, emit rays which cause electrified bodies to lose their electric charges, and act on photographic plates that are wrapped in sheets of black paper, or in thin sheets of other substances which stop rays of light. The radioactivity of salts of uranium was proved not to be increased or diminished when these salts had been shielded for 5 years from the action of light by keeping them in leaden boxes. Shortly after Becquerel's discovery, experiments proved that salts of the rare metal thorium are radioactive. This discovery was followed by Madame Curie's demonstration of the fact that certain specimens of pitchblende, a mineral which contains compounds of uranium and of many other metals, are extremely radioactive, and by the separation from pitchblende by Monsieur and Madame Curie of new substances much more radioactive than compounds of uranium or of thorium. The new substances were proved to be compounds chemically very similar to salts of barium. Their compositions were determined on the supposition that they were salts of an unknown metal closely allied to barium. Because of the great radioactivity of the compounds, the hypothetical metal of them was named radium. At a later time, radium was isolated by Madame Curie. It is described by her as a white, hard, metal-like solid, which reacts with water at the ordinary temperature, as barium does. Since the discovery of radium compounds, many radioactive substances have been isolated. Only exceedingly minute quantities of any of them have been obtained. The quantities of substances used in experiments on radioactivity are so small that they escape the ordinary methods of measurement, and are scarcely amenable to the ordinary processes of the chemical laboratory. Fortunately, radioactivity can be detected and measured by electrical methods of extraordinary fineness. Methods the delicacy of which very much more exceeds that of spectroscopic methods, than the sensitiveness of these surpasses that of ordinary chemical analysis. At the time of the discovery of radioactivity, about 75 substances were called elements. In other words, about 75 different substances were known to chemists, none of which had been separated into unlike parts, none of which had been made by the coalescence of unlike substances. Compounds of only 2 of these substances, uranium and thorium, are radioactive. Radioactivity is a very remarkable phenomenon. So far as we know at present, radioactivity is not a property of the substances which form almost the whole of the rocks, the waters, and the atmosphere of the earth. It is not a property of the materials which constitute living organisms. It is a property of some 30 substances. Of course the number may be increased. A few of which are found widely distributed in rocks and waters, but none of which is found anywhere except in extraordinarily minute quantity. Radium is the most abundant of these substances, but only a very few grains of radium chloride can be obtained from a couple of tons of pitchblende. In Chapter 10 of The Story of the Chemical Elements, I have given a short account of the outstanding phenomena of radioactivity. For the present purpose, it will suffice to state a few facts of fundamental importance. Radioactive substances are stores of energy, some of which is constantly escaping from them. They are constantly changing without external compulsion, and are constantly radiating energy. All explosives are storehouses of energy which, or part of which, can be obtained from them, but the liberation of their energy must be started by some kind of external shock. When an explosive substance has exploded, its existence as an explosive is finished. The products of the explosion are substances from which energy cannot be obtained. When a radioactive substance has exploded, it explodes again, and again, and again. A time comes, sooner or later, when it has changed into substances that are useless as sources of energy. The disintegration of an explosive, started by an external force, is generally completed in a fraction of a second. Change of condition changes the rate of explosion. The half-life period of each radioactive substance is a constant characteristic of it. If a gram of radium were kept for about 1,800 years, half of it would have changed into radio-inactive substances. Conditions may be arranged so that an explosive remains unchanged. Wet gun cotton is not exploded by a shock which would start the explosion of dry gun cotton. In other words, the explosion of an explosive can be regulated. The explosive changes of a radioactive substance which are accompanied by the radiation of energy cannot be regulated. They proceed spontaneously in a regular and definable manner, which is not influenced by any external conditions, such as great change of temperature, presence or absence of other substances. so far as these conditions have been made the subject of experiment. The amount of activity of a radioactive substance has not been increased or diminished by any process to which the substance has been subjected. Explosives are manufactured articles. Explosiveness is a property of certain arrangements of certain quantities of certain elements. So far as experiments have gone, it has not been found possible to add the property of radioactivity to an inactive substance, or to remove the property of radioactivity from an active substance. The cessation of radioactivity of an active substance is accompanied by the disappearance of the substance, and the production of inactive bodies altogether unlike the original active body. Radioactive substances are constantly giving off energy in the form of heat, sending forth rays which have definite and remarkable properties, and producing gaseous emanations which are very unstable, and change, some very rapidly, some less rapidly, into other substances, and emit rays which are generally the same as the rays emitted by the parent substance. In briefly considering these three phenomena, I shall choose radium compounds as representative of the class of radioactive substances. Radium compounds spontaneously give off energy in the form of heat. A quantity of radium chloride which contains 1 gram of radium continuously gives out per hour a quantity of heat sufficient to raise the temperature of 1 gram of water through 100 degrees centigrade, or 100 grams of water through 1 degree centigrade. The heat given out by 1 gram of radium during 24 hours would raise the temperature of 2,400 grams of water through 1 degree centigrade. In 1 year, the temperature of 876,000 grams of water would be raised through 1 degree centigrade, and in 1800 years, which is approximately the half-life period of radium, the temperature of 1,576,800 kilograms of water would be raised through 1 degree centigrade. These results may be expressed by saying that if 1 gram, about 15 grains, of radium were kept until half of it had changed into inactive substances, and if the heat spontaneously produced during the changes which occurred were caused to act on water, that quantity of heat would raise the temperature of about 15½ tons of water from its freezing to its boiling point. Radium compounds send forth 3 kinds of rays, distinguished as alpha, beta, and gamma rays. Experiments have made it extremely probable that the alpha rays are streams of very minute particles, somewhat heavier than atoms of hydrogen, moving at the rate of about 18,000 miles per second, and that the beta rays are streams of much more minute particles, the mass of each of which is about 1/1000th of the mass of an atom of hydrogen, moving about 10 times more rapidly than the alpha particles, that is, moving at the rate of about 180,000 miles per second. The gamma rays are probably pulsations of the ether, the medium supposed to fill space. The emission of alpha rays by radium is accompanied by the production of the inert elementary gas, helium. Therefore the alpha rays are, or quickly change into, rapidly moving particles of helium. The particles which constitute the beta rays carry electric charges. These electrified particles, each approximately 1,000 times lighter than an atom of hydrogen, moving nearly as rapidly as the pulsations of the ether, which we call light, are named electrons. The rays from radium compounds discharge electrified bodies, ionize gases, that is, cause them to conduct electricity, act on photographic plates, and produce profound changes in living organisms. The radium emanation is a gas about 111 times heavier than hydrogen. To this gas Sir William Ramsay has given the name niton. The gas has been condensed to a colourless liquid and frozen to an opaque solid, which glows like a minute arc light. Radium emanation gives off alpha particles, that is, very rapidly moving atoms of helium, and deposits exceedingly minute quantities of a solid radioactive substance known as radium A. The change of the emanation into helium and radium A proceeds fairly rapidly. The half-life period of the emanation is a little less than 4 days. This change is attended by the liberation of much energy. The only satisfactory mental picture which the facts allow us to form at present of the emission of beta rays from radium compounds is that which represents these rays as streams of electrons, that is, particles each about 1,000 times lighter than an atom of hydrogen, each carrying an electric charge, and moving at the rate of about 180,000 miles per second, that is, nearly as rapidly as light. When an electric discharge is passed from a plate of metal, arranged as the cathode, to a metallic wire, arranged as the anode, both sealed through the walls of a glass tube or bulb, from which almost the whole of the air has been extracted, rays proceed from the cathode in a direction at right angles thereto, and striking the glass in the neighbourhood of the anode, produce a green phosphorescence. Facts have been gradually accumulated which force us to think of these cathode rays as streams of very rapidly moving electrons, that is, as streams of extraordinarily minute electrically charged particles, identical with the particles which form the beta rays emitted by compounds of radium. The phenomena of radioactivity, and also the phenomena of the cathode rays, have obliged us to refine our machinery of minute particles by including therein particles at least 1,000 times lighter than atoms of hydrogen. The term electron was suggested a good many years ago by Dr. Johnston Stoney for the unit charge of electricity which is carried by an atom of hydrogen when hydrogen atoms move in a liquid or gas under the directing influence of the electric current. Some chemists speak of the electrons, which are the beta rays from radium, and the cathode rays produced in almost vacuous tubes, as non-material particles of electricity. Non-material means devoid of mass. The method by which approximate determinations have been made of the charges on electrons consists in measuring the ratio between the charges and the masses of these particles. If the results of the determinations are accepted, electrons are not devoid of mass. Electrons must be thought of as material particles, differing from other minute material particles in the extraordinary smallness of their masses, in the identity of their properties, including their mass, in their always carrying electric charges, and in the vast velocity of their motion. We must think of an electron either as a unit charge of electricity, one property of which is its minute mass, or as a material particle having an extremely small mass and carrying a unit charge of electricity. The two mental pictures are almost, if not quite, identical. Electrons are produced by sending an electric discharge through a glass bulb containing a minute quantity of air or other gas, using metallic plates or wires as cathode and anode. Experiments have shown that the electrons are identical in all their properties, whatever metal is used to form the cathode and anode, and of whatever gas there is a minute quantity in the bulb. The conclusions must be drawn that identical electrons are constituents of, or are produced from, very different kinds of chemical elements. As the facts about cathode rays and the facts of radioactivity are, at present, inexplicable, except on the supposition that these phenomena are exhibited by particles of extraordinary minuteness, and as the smallest particles with which chemists are concerned in their everyday work are the atoms of the elements, we seem obliged to think of many kinds of atoms as structures, not as homogeneous bodies. We seem obliged to think of atoms as very minute material particles, which either normally are, or under definite conditions may be, associated with electrically charged particles very much lighter than themselves, all of which are identical, whatever be the atoms with which they are associated, or from which they are produced. In their study of different kinds of matter, chemists have found it very helpful to place in one class those substances which they have not been able to separate into unlike parts. They have distinguished this class of substances from other substances, and have named them elements. The expression chemical elements is merely a summary of certain observed facts. For many centuries, chemists have worked with a conceptual machinery based on the notion that matter has a grained structure. For more than 100 years they have been accustomed to think of atoms as the ultimate particles with which they have had to deal. Working with this order-producing instrument, they have regarded the properties of elements as properties of the atoms, or of groups of a few of the atoms, of these substances. That they might think clearly and suggestively about the properties of elements, and connect these with other chemical facts, They have translated the language of sense perceptions into the language of thought, and for properties of these substances which have not been decomposed, have used the more fertile expression, atomic properties. When a chemist thinks of an atom, he thinks of the minutest particle of one of the substances which have the class mark "have not been decomposed," and the class name element. The chemist does not call these substances elements because he has been forced to regard the minute particles of them as undivided, much less because he thinks of these particles as indivisible. His mental picture of their structure as an atomic structure formed itself from the fact that they had not been decomposed. The formation of the class element followed necessarily from observed facts, and has been justified by the usefulness of it as an instrument for forwarding accurate knowledge. The conception of the elementary atom as a particle which had not been decomposed followed from many observed facts beside those concerning elements, and has been justified by the usefulness of it as an instrument for forwarding accurate knowledge. Investigations proved radioactivity to be a property of the very minute particles of certain substances, and each radioactive substance to have characteristic properties, among which were certain of those that belong to elements, and to some extent are characteristic of elements. Evidently, the simplest way for a chemist to think about radioactivity was to think of it as an atomic property. Hence, as atomic properties had always been regarded in the last analysis as properties of elements, it was natural to place the radioactive substance in the class elements, provided that one forgot for the time that these substances have not the class mark "have not been decomposed." As the facts of radioactivity led to the conclusion that some of the minute particles of radioactive substances are constantly disintegrating, and as these substances had been labelled elements, it seemed probable, or at least possible, that the other bodies which chemists have long called elements are not true elements, but are merely more stable collocations of particles than the substances which are classed as compounds. As compounds can be changed into certain other compounds, although not into any other compounds, a way seemed to be opening which might lead to the transformation of some elements into some other elements. The probability that one element might be changed into another was increased by the demonstration of the connections between uranium and radium. The metal uranium has been classed with the elements since it was isolated in 1840. In 1896, Becquerel found that compounds of uranium, and also the metal itself, are radioactive. In the light of what is now known about radioactivity, it is necessary to suppose that some of the minute particles of uranium emit particles lighter than themselves, and change into some substance or substances different from uranium. In other words, it is necessary to suppose that some particles of uranium are spontaneously disintegrating. This supposition is confirmed by the fact, experimentally proved, that uranium emits alpha rays, that is, atoms of helium, and produces a substance known as uranium X. Uranium X is itself radioactive. It emits beta rays, that is, it gives off electrons. Inasmuch as all minerals which contain compounds of uranium contain compounds of radium also, it is probable that radium is one of the disintegration products of uranium. The rate of decay of radium may be roughly expressed by saying that if a quantity of radium were kept for 10,000 years, only about 1% of the original quantity would then remain unchanged. Even if it were assumed that at a remote time the Earth's crust contained considerable quantities of radium compounds, it is certain that they would have completely disappeared long ago had not compounds of radium been reproduced from other materials. Again, the most likely hypothesis is that compounds of radium are being produced from compounds of uranium. Uranium is a substance which, after being rightly classed with the elements for more than half a century, because it had not been separated into unlike parts, must now be classed with the radium-like substances which disintegrate spontaneously, although it differs from other radioactive substances in that its rate of change is almost infinitively slower than that of any of them, except thorium. Footnote: the life period of uranium is probably about 8,000 million years. End footnote. Thorium, a very rare metal, is the second of the 75 or 80 elements known when radioactivity was discovered, which has been found to undergo spontaneous disintegration with the emission of rays. The rate of change of thorium is considerably slower than that of uranium. Footnote: the life period of thorium is possibly about 40,000 million years. End footnote. Reader's note: the author is apparently referring to half-lives. End reader's note. None of the other substances placed in the class of elements is radioactive. On page 192 I said that when the radioactive substances had been labelled elements, the facts of radioactivity led some chemists to the conclusion that the other bodies which had for long been called by this class name, or at any rate some of these bodies, are perhaps not true elements, but are merely more stable collocations of particles than the substances called compounds. It seems to me that this reasoning rests on an unscientific use of the term element. It rests on giving to that class name the meaning substances asserted to be undecomposable. A line of demarcation is drawn between elements, meaning thereby forms of matter said to be undecomposable, but probably capable of separation into unlike parts, and true elements, meaning thereby groups of identical undecomposable particles. If one names the radioactive substances elements, one is placing in this class substances which are specially characterized by a property the direct opposite of that, the possession of which by other substances was the reason for the formation of the class. To do this may be ingenious. It is certainly not scientific. Since the time of Lavoisier, since the last decade of the 18th century, careful chemists have meant by an element a substance which has not been separated into unlike parts, and they have not meant more than that. The term element has been used by accurate thinkers as a useful class mark, which connotes a property, the property of not having been decomposed, common to all substances placed in the class, and differentiating them from all other substances. Whenever chemists have thought of elements as the ultimate kinds of matter with which the physical world is constructed, and they have occasionally so thought and written, they have fallen into quagmires of confusion. Of course, the elements may some day be separated into unlike parts. The facts of radioactivity certainly suggest some kind of inorganic evolution. Whether the elements are decomposed is to be determined by experimental inquiry, remembering always that no number of failures to simplify them will justify the assertion that they cannot be simplified. Chemistry neither asserts or denies the decomposability of the elements. At present we have to recognize the existence of extremely small quantities, widely distributed in rocks and waters, of some 30 substances, the minute particles of which are constantly emitting streams of more minute identical particles that carry with them very large quantities of energy, all of which 30 substances are characterized and are differentiated from all other classes of substances wherewith chemistry is concerned by their spontaneous mutability, and each is characterized by its special rate of change and by the nature of the products of its mutations. We have now to think of the minute particles of 2 of the 75 or 80 substances which, until the other day, had not been decomposed, and were therefore justly called elements, as very slowly emitting streams of minuter particles, and producing characteristic products of their disintegration. And we have to think of some 80 substances as particular kinds of matter, at present properly called elements, because they are characterized and are differentiated from all other substances by the fact that none of them has been separated into unlike parts. The study of radioactivity has introduced into chemistry and physics a new order of minute particles. Dalton made the atom a beacon light, which revealed to chemists paths that led them to wider and more accurate knowledge. Avogadro illuminated chemical and also physical ways by his conception of the molecule as a stable, although separable, group of atoms, with particular properties different from those of the atoms which constituted it. The work of many investigators has made the old paths clearer, and has shown to chemists and physicists ways they had not seen before, by forcing them to think of, and to make use of, a third kind of material particles, that are endowed with the extraordinary property of radioactivity. Dalton often said, "Thou knowest thou canst not cut an atom," but the fact that he applied the term atom to the small particles of compounds proves that he had escaped the danger of logically defining the atom, the danger of thinking of it as a particle which never can be cut. The molecule of Avogadro has always been a decomposable particle. The peculiarity of the new kind of particles, the particles of radioactive bodies, is, not that they can be separated into unlike parts by the action of external forces, but that they are constantly separating of their own accord into unlike parts, and that their spontaneous disintegration is accompanied by the production of energy, the quantity of which is enormous in comparison with the minuteness of the material specks which are the carriers of it. The continued study of the properties of the minute particles of radioactive substances, a new name is needed for those most mutable of material grains, must lead to discoveries of great moment for chemistry and physics. That study has already thrown much light on the phenomena of electric conductivity. It has given us the electron, a particle at least 1,000 times lighter than an atom of hydrogen. It has shown us that identical electrons are given off by, or are separated from, different kinds of elementary atoms, under definable conditions. It has revealed unlooked-for sources of energy. It has opened and begun the elucidation of a new department of physical science. It has suggested a new way of attacking the old problem of the alchemists, the problem of the transmutation of the elements. The minute particles of two of the substances for many years classed as elements give off electrons. Uranium and thorium are radioactive. Electrons are produced by sending an electric discharge through very small traces of different gases, using electrodes of different metals. Electrons are also produced by exposing various metals to the action of ultraviolet light, and by raising the temperature of various metals to incandescence. Electrons are always identical, whatever be their source. Three questions suggest themselves. Can the atoms of all the elements be caused to give off electrons? Are electrons normal constituents of all elementary atoms? Are elementary atoms co-locations of electrons? These questions are included in the demand, is it possible to imagine a model which has in it the potentiality of explaining radioactivity and other allied phenomena, as well as all other chemical and physical properties of elements and compounds? These questions are answerable by experimental investigation, and only by experimental investigation. If experimental inquiry leads to affirmative answers to the questions, we shall have to think of atoms as structures of particles much lighter than themselves. We shall have to think of the atoms of all kinds of substances, however much the substances differ chemically and physically, as co-locations of identical particles. We shall have to think of the properties of atoms as conditioned in our final analysis by the number and arrangement of their constitutive electrons. Now, if a large probability were established in favour of the view that different atoms are co-locations of different numbers of identical particles, or of equal numbers of differently arranged identical particles, we should have a guide which might lead to methods whereby one co-location of particles could be formed from another co-location of the same particles, a guide which might lead to methods whereby one element could be transformed into another element. To attempt to imagine a model which has in it the potentiality of explaining radioactivity, the production of cathode rays, and the other chemical and physical properties of elements and compounds, might indeed seem to be a hopeless undertaking. A beginning has been made in the mental construction of such a model by Professor Sir J. Thomson. To attempt a description of his reasoning and his results is beyond the scope of this book. The facts that the emanation from radium compounds spontaneously gives off very large quantities of energy, and that the emanation can easily be brought into contact with substances on which it is desired to do work, suggested to Sir William Ramsay that the transformation of compounds of one element into compounds of another element might possibly be effected by enclosing a solution of a compound along with radium emanation in a sealed tube, and leaving the arrangement to itself. Under these conditions, the molecules of the compound would be constantly bombarded by a vast number of electrons shot forth at enormous velocities from the emanation. The notion was that the molecules of the compound would break down under the bombardment, and that the atoms so produced might be knocked into simpler groups of particles, in other words, changed into other atoms by the terrific silent shocks of the electrons fired at them incessantly by the disintegrating emanation. Sir William Ramsay regards his experimental results as establishing a large probability in favour of the assertion that compounds of copper were transformed into compounds of lithium and sodium, and compounds of thorium, of cerium, and of certain other rare metals into compounds of carbon. The experimental evidence in favour of this statement has not been accepted by chemists as conclusive. A way has, however, been opened which may lead to discoveries of great moment. Let us suppose that the transformation of one element into another element, or into other elements, has been accomplished. Let us suppose that the conception of elementary atoms as very stable arrangements of many identical particles, from about 1,000 to about 250,000 times lighter than the atoms, has been justified by crucial experiments. Let us suppose that the conception of the minute grains of radioactive substances as particular but constantly changing arrangements of the same identical particles, stable groups of which are the atoms of the elements, has been firmly established. One result of the establishment of the electronic conception of atomic structure would be an increase of our wonder at the complexity of nature's ways, and an increase of our wonder that it should be possible to substitute a simple, almost rigid, mechanical machinery for the ever-changing flow of experience, and by the use of that mental mechanism not only to explain very many phenomena of vast complexity, but also to predict occurrences of similar entanglement, and to verify these predictions. The results which have been obtained in the examination of radioactivity, of cathode rays, of spectra at different temperatures, and of phenomena allied to these, bring again into prominence the ancient problem of the structure of what we call matter. Is matter fundamentally homogeneous or heterogeneous? Chemistry studies the relations between the changes of composition and the changes of properties which happen simultaneously in material systems. The burning fire of wood, coal, or gas, the preparation of food to excite and to satisfy the appetite, the change of minerals into the iron, steel, copper, brass, lead, tin, lighting, burning and lubricating oils, dyestuffs and drugs of commerce, the change of the skins, wool and hair of animals, and of the seeds and fibres of plants, into clothing for human beings, the manufacture from rags, grass, or wood of a material fitted to receive and to preserve the symbols of human hopes, fears and aspirations, love and hate, pity and aversion, the strange and most delicate processes which, happening without cessation in plants and animals and men, maintain that balanced equilibrium which we call life, and when the silver cord is being loosed and the bowl broken at the cistern, the awful changes which herald the approach of death. Not only the growing grass in midsummer meadows, not only the coming of autumn, in dyed garments, travelling in the glory of his apparel, but also the opening buds, the pleasant scents, the tender colours which stir our hearts in the springtime, the only pretty ring-time, when birds do sing ding-a-dong-ding. These and 1,000 other changes have all their aspects which it is the business of the chemist to investigate. Confronted with so vast a multitude of never-ceasing changes, and bidden to find order there, if he can, bidden, rather compelled by that imperious command which forces the human mind to seek unity in variety, and, if needs be, to create a cosmos from a chaos, no wonder that the early chemists jumped at the notion that there must be, that there is, some one thing, some universal essence, which binds into an orderly whole the perplexing phenomena of nature, some water of paradise, which is for the healing of all disorder, some well at the world's end, a draught whereof shall bring peace and calm security. The alchemists set forth on the quest. Their quest was barren. They made the great mistake of fashioning the one thing, the essence, the water of paradise, from their own imaginings of what nature ought to be. In their own likeness they created their goal, and the road to it. If we are to understand nature, they cried, her ways must be simple, therefore her ways are simple. Chemists are people of a humbler heart. Their reward has been greater than the alchemists dreamed. By selecting a few instances of material changes, and studying these with painful care, they have gradually elaborated a general conception of all those transformations wherein substances are produced unlike those by the interaction of which they are formed. That general conception is now both widening and becoming more definite. Today, chemists see a way opening before them which they reasonably hope will lead them to a finer, a more far-reaching, a more suggestive, at once a more complex and a simpler conception of material changes than any of those which have guided them in the past. The end of The Story of Alchemy and the Beginnings of Chemistry.